Aloha, or whatever in the world they say in Aruba. If you're watching this, that means that you have already done the warm-up. You've read the chapter section 2 on the first law of thermodynamics, and now you're watching the video. If you haven't done those other things, you need to do that before you watch this, because I'm just going to kind of summarize things again for you to kind of round out some stuff for your thinking about thermodynamics. Okay, you see up here on my little sticky note here some things that you're going to need your handout, and we're going to be looking at pages 7 to 17, and then there's some schematic drawings at the end of your handouts, pages 28 to 31, that you're going to need to look at and study. There's how a refrigerator works and how a gas engine cycle works as well. Then you're going to need to take notes. Remember, pause is your friend. You can always stop and go back, or just stop and stare at the wall, or stop and go get some food, whatever you need to do. All right, let's get started. Let me turn that thing off, get that out of the way. And I would like you to first look at these objectives here. First, we're going to illustrate how the first law of thermodynamics is a statement of energy conservation. We're going to use the roller coaster illustration, and that'll help us derive the formula. I'll show you some notes on that formula and how it applies to different thermodynamic processes. If you go back to your handouts and you look at page 7, I've written in on the next to the definitions for isovolumetric, isothermal, and adiabatic, I've written into you like the conditions and how that applies to that formula. Secondly, calculate heat work and the change in internal energy by applying the first law of thermodynamics. You're going to want to study that, study the sample problem that's in the handouts before you try anything, like before you do the practice B problems 1, 3, and 5. But definitely work through that. I'm not going to go over that with you. It's all right there. You can look at it yourself. And then thirdly, applying the first law of thermodynamics to describe cyclic processes. We'll just do that by demonstrating how the cyclic processes work and how that relates to thermodynamics. Okay, so let me go to our first other slide here. There we go. About energy conservation. That no matter what, you've got all kinds of lost energy. You're going to have friction. You're going to have heat being expended to your car, making it warmer. We talked about that the other day. And so if friction is taken into account, mechanical energy is not conserved. All your potential energy does not turn into kinetic energy. So we're going to look at this roller coaster here and see how this works. Oh, I got to go to the slideshow now. Okay, here we go.
The total energy in a closed system is always conserved, although it may be converted into other forms. While this roller coaster car is being raised up, energy is being added to the car from an outside source. This is not a closed system. The potential energy gained is shown by the red bar on the graph. After the car is released from the top of the hill, we will assume that the only source of friction is at the axles of the roller coaster wheels. Since nothing is adding or taking away energy from the car, it can be considered a closed system for the rest of our example. As the cart goes down the hill, its potential energy is converted into kinetic energy. Kinetic energy is shown by the blue bar. Gradually, friction at the axles causes heating. This change in internal energy is shown by the green bar. By the end of the run, most of the mechanical energy has been converted into internal energy. At all times after the first hill, the total energy remains the same.
Dumping all that heat all over the place. That's why your tires get warm after being run and all that kind of stuff. All right, if you go and you check out page 7 in your stuff, and then now's the chance to get out your paper and your pencil to take some notes. We want to see where in the world that formula comes from. Is they show those 3 pieces there in the roller coaster. To see how they're related, and then what happens when you have an adiabatic process or when you have an isothermal process. How does that affect that formula? So here's a couple of definitions for thermodynamics, and you can pause and you can copy this stuff down because I'm going to read really fast. The quantity of heat supplied to any isolated system, you know that word now, in the form of heat is equal to the work done by the system plus the change in internal energy of the system. You can see that down here in the formula. Q is heat. Right here we've got the change in internal energy, and here plus W, there's our work. Or we could say it like this: when heat is converted to another form of energy, or when other forms of energy are converted to heat, there is no loss of energy. So stated algebraically, Q is the amount of heat, E sub I is the initial total internal energy, E sub F is the new internal energy after the increase or decrease in temperature, and W is work. So the change in energy there is equal to delta U. So Q equals delta U plus W. And any heat added to the system is going to make the thing do work. And it might increase the internal temperature as well, the internal energy. Q is positive when heat gets added, because Q is heat. W is positive when the body does work on the surrounding objects. If no work is done, in the situation we had isovolumetric, where there's no change in volume, then delta U equals Q, heat added and removed. For example, heating water and there's no phase change, so there's no change in the volume. Again, look back at page 7. I've listed next to each of those definitions of the processes what's going on there. So for instance, for isovolumetric, if delta V equals 0, then P delta V equals 0, and that was equal to work. There's no work, so we put a 0 into the equation where W was, and off we go. We get the first law of thermodynamics equation, just all the pieces get moved around and we apply it to that particular situation. So here's an example of adiabatic. Q equals 0 because there's no heat added or taken away from it because it happens really fast. So where Q was goes a 0, and then we take the equation and we move it around so that it states it like this. Any change in internal energy means that work is done on the system. It gets squeezed or something like that. There's a change in internal energy. There's stuff from yesterday, and then on down here. So we're going to move on to talking about these internal combustion engines and just heat transfer mechanisms. Could be burning coal in a locomotive or whatever the case may be, but any device that converts heat energy into mechanical energy is called a heat engine. Generally speaking, in an engine that the working parts are taken through a series of operations known as a cycle, and we'll be looking at that in a minute. But some energy from a high temperature source is converted into work done, but not all the heat supplied to the engine is turned into work. The heat that's not converted to work is delivered by the engine to some external reservoir called a heat sink, and so we have this schematic. You might want to go ahead and pause right now and ponder that and write it down. Now, this is just a schematic. This is just kind of the concept thing. The hot part could be inside the boiler. It could be inside the engine. It could be whatever, as long as you're adding heat to it. And then we see that only some of it's going to be turned into work, and then the rest of it gets lost, whether it's to the engine parts or out the exhaust pipe, whatever the case may be. In an ideal engine, the wasted heat is somehow returned to the high temperature heat source and reused. You're going to read about things that have tried to do that, like especially the Stirling engine. So when you read the article tomorrow or in the next phase, you definitely want to focus on that one in this context. You want to see how that works to try to get the cold, to take this lost energy and to plunk it back up here and see if we can reuse it. Okay, back to our little presentation here. There's energy conservation. You might want to look at that. That's all right. That's in your handouts as well. Go through the sample problem, which I'm not going to do right now, and understand this. I kind of summarized this page on page 7 of your handouts. Go ahead and play this one so you can hear what they have to say about this.
The first law of thermodynamics states that the change in internal energy in a system is equal to the energy transferred to or from the system as heat, minus the work done on or by the system. Isovolumetric means same volume. Since the volume does not change, no work is done. If energy is added to the system as heat, the system's internal energy increases. If energy is removed from the system as heat, its internal energy decreases. Isothermal means same temperature. There can be no change in the internal energy of a system. The energy transferred to the system as heat may be removed as work done by the system, or the energy added to the system as work done on it may be removed from the system as heat. In an adiabatic process, there is no transfer of energy as heat. If work is done on the system, its internal energy increases, or if work is done by the system, its internal energy decreases. By definition, in an isolated system there is no heat or work interaction with the surroundings. According to the first law of thermodynamics, there is no change in the internal energy of an isolated system.
Yeah, how many of those are there, right? These next couple of slides in your things, you're gonna look at them, and I'd like you to study this page right here in your handout. I want you to understand it, and you want to study this one. You can do that later. I'll go ahead and let them play this stuff so you can see the animation of how that internal engine works.
Combustion engines convert chemical energy into work energy. Let's consider the four-cycle gasoline engine found in most vehicles. During the intake stroke, the cylinder descends, taking in a fuel-air mixture from the fuel injector or carburetor. Then, in the compression stroke, the mixture is compressed. This raises its temperature and makes it easier to ignite. A spark produces combustion and begins the combustion stroke. This is when the engine is doing useful work. Now the chemicals are burned up and need to be removed. This is done during the exhaust stroke. Then the cycle is ready to begin again. 3 of the 4 cycles of this engine are just housekeeping. Only the combustion stroke involves an important transformation of energy. In this stroke, the chemical potential energy of the gasoline is turned into mechanical work.
And let's go to our other slide where you got a refrigerator. How does a refrigerator work? I bet Butch would like to know about this, right? Him and his relationship. Alright, here we go.
The natural flow of energy as heat is always from a warmer object to a cooler object. In a refrigerator, the opposite occurs. A refrigerator does work in order to transfer energy from a low temperature region inside of the refrigerator to a high temperature region outside the refrigerator. A refrigerator contains a closed circuit of tubing filled with a liquid known as refrigerant. Let's start with the refrigerant at this point. It is in a liquid state at a low temperature and pressure. It is colder than the air inside the refrigerator. The refrigerant absorbs energy as heat from the refrigerator's interior and lowers the temperature of the items in the fridge. The transfer of energy to the refrigerant increases its temperature and causes the refrigerant to boil. By the time it reaches the compressor, it is a gas at moderate temperature and low pressure. The compressor does work on the gas while compressing it. No energy enters the gas as heat, so this is an adiabatic process. The compression increases the pressure, internal energy, and temperature of the gas. The gas is pushed into pipes that are mounted on the back of the refrigerator. The pipes are exposed to room air at a lower temperature than the gas, and therefore the gas transfers energy to the outside of the refrigerator. As it releases energy to the room, the gas cools and condenses back into a liquid. The high-pressure liquid then squirts through an expansion valve. Its volume increases. While expanding, the gas does work on its surroundings. Its internal energy decreases rapidly. It is now at a low temperature, again ready to absorb energy from the inside of the refrigerator.
And there you go. Now you know how to be a refrigerator repairman. That's it for today. Tune back in next time for more adventures in Chapter 10.